Let's learn how to integrate two types of integrals. The first one will be a definite integral, second one will be indefinite, starting with the first one on the left here. So the only thing that distinguishes definite from indefinite is whether they have bounds of integration, top and bottom of that integral sign. So for this one, I'm going to use a reverse power rule to integrate this function. So for that, the power rule for integration, the exact opposite of the power rule for differentiation, where we put down the exponent and then subtract 1, whereas in this case, since we are taking an integral, not a derivative, if the function is of the form x to the power of a, then the antiderivative can be written as x to that same power plus 1 over that new power, a plus 1. So we'll use that on the side here for each of these parts of the function. So x to the third, I'm going to turn that to x to the 3 plus 1 over 3 plus 1. The x squared becomes also a new power, 1 added to it and divided by that new power. And there's no power here, but there's an invisible 1 there, so we add 1 to that, divide by that new exponent. Okay, so you can simplify this notation here and also rewrite everything without all the plus signs. Great. And this is going from -1 to 1, so typically after we finish an integral, if it was an indefinite integral, another distinction here is we would write plus c at the end. However, since this is definite, we don't do that step. Instead, we are going to evaluate at the bounds like so. Right, so we start with the higher bound of integration, plug it into all of these values, and that's going to create some expression in these parentheses. And then we're going to subtract the value we get once we plug in the -1 thereafter into all of these parts of the function. So I'll start with the upper bound of integration and plug in 1 everywhere I see an x. Okay, and then I'm going to plug in the -1 everywhere that I see an x. I do realize I could have simplified that 4 over 2 at the end there. So you can do that if you'd like. And now we're just going to evaluate, simplify everything using order of operations. So I should get in this parentheses much more simplified result, 1 over 4 minus 2 over 3 plus 4 over 2, and you could simplify that to just a 2. Okay, and then this right side, 1 over 4 positive, this becomes a -1, so -1 times -2 is a positive 2, and the 3 in the denominator, plus 4 over 2 becomes another simplified 2. Okay, we're getting closer to our final answer. If we just distribute this negative out throughout everything, we don't need the parentheses on the first value. -2. You see you get a lot of cancellations. The 1/4 are gone. The 2 and the -2 are also gone. Share the same value, but different signs. And so we just end up with a double of the -2/3. So the final answer for this integral is a negative 4/3. A definite integral will always end up with a definite answer, or final numerical value. It represents an area underneath that curve between -1 and 1. Moving over to an indefinite integral, let's look at this example. Okay, so it has a few shorter steps for this one. To integrate this, instead of using a reverse power rule, I'm going to utilize a U substitution. Another integration technique. Right? So let U equal some value, some part of the function. And we're going to have du be the derivative of that function that we choose. Sometimes it's the entire function in the integral. Sometimes it's part of it. Usually we're gonna use a specific part. And from there, we're going to put everything in terms of u, integrate, which will be a much simpler function, and then put everything back in terms of x at the end. And in this case, we get to pick, right? So this is a decision we make. We get to pick what is going to be the u function. There is some discernment there of what will make it an easier substitution. So for example, if I just let u equal x, I have a not so simplified new u substitution. It ends up being the same function again, right? So we want to be a little bit clever of how we can make this integration a bit easier. What I'm going to do is let u equal this entire expression, x plus 4. So I'll make a little chart for myself. U is equal to x plus 4. So then we're going to figure out what du is equal to. The derivative of x plus 4, we get 1 for the derivative of x, and then 4 has a 0 derivative. Now, typically you could write du with respect to x, but if you move this over, then we're able to make even more replacements in the integral itself since the dx is present there. So in u substitution, you'll typically see instead of the dx at the bottom in the traditional derivative fashion, you'll rewrite u and du in this way. In fact, 1 times anything is itself, so you could just write that du is equal to dx. Okay, so let's see how this restructures our integral, hopefully makes it a bit simpler. We have another way to write the integral. I didn't do any u replacement yet, but I want us to see how we're going to incorporate the u in here. So this entire thing can be rewritten as just u, and the dx out here that I've separated from the fraction can be rewritten as du, so that we have no presence of x whatsoever. And that is a bit simpler because I can also rewrite this if you prefer, like me, to see this as a non-fraction function, right? Just see it almost like an exponent form. Then we have u to the -3rd, another way to write 1 over u to the power of 3. Switch it from a denominator to a numerator. And now we can utilize that reverse power rule for integration like we did in the last one in the definite integral. And so we want to be careful since this is a negative exponent this time. So we would use that reverse power rule of adding 1 and dividing by that new exponent. So this becomes u to the -2 over -2. If you want to put it back in fraction form, that's 1 over -2 u squared. But we always have to remember the last part for u substitution to put back in terms of x. Okay, so then we have to recall from our initial substitution, u is equal to x plus 4. And the very last step here would be to, I should say, penultimate step, because as a reminder of what we do with indefinite integrals, such as this one that had no bounds of integration, our work gets cut short for us here, because instead of having to plug in an upper and lower bound, this new antiderivative that we just found simply needs a plus c at the end, and then we're done. So those are the steps for either evaluating or integrating both a definite and indefinite integral.